Periodic functions, graphs of sine and cosine. So a periodic function is quite simply just a function that repeats the exact same pattern over a certain period. All these three examples you see on your book are not periodic functions. They have no repeating pattern. They just go in a certain trend. So these functions follow a certain trend. Here we have a conic, a linear, an exponential. Now we're going to learn about periodic functions. This is a periodic function, and this is actually the graph of the function of sine, or sine of theta. And we see here the period is that in every 360 degrees it repeats. So if we were to go from 0 to 360, it goes up, down, up, and then it starts right at 0 again. It's going to repeat. If we start from negative 360, it goes up, down, down, up. So in the period of 360 degrees, the function repeats the exact same pattern, the exact same values over and over and over and over again. It does not end. So that's the period. That's a periodic function, and the graphs of sine and cosine are what we call sinusoids, or sinus. Hey, look, there it is. That word, the bold one. Let me focus in on it. Hold on. Sinusoid. Sinusoid. I can't say it. But we call sinusoids pretty much the graph of any wibbly wobbly line. So any line that kind of does waves, or like this, for example. This is the graph of a sinusoid. It can be periodic, or it can be, just wavy. So a sinusoid is any wavy graph, more or less. Now let's get on to the graphs of cosine and sine. Instead of doing that, where do we have it? What are we looking for? Okay, I'm just going to draw it. So I'll have my unit circle right here as a reference, and we'll start with the graph of sine. Now sinusoid functions are pretty long horizontally, so let me get my mini ruler so I can make this semi-straight. So I'll go ahead and make this a pretty long coordinate plane as far as the x-axis goes. The y-axis can be pretty normal. I'll just make it like that. And I'm going to go ahead and I'm going to graph sine for the first, let's just say the first 360 degrees. I'll make this pretty narrow. So this will be positive 1. This will be negative 1. We'll make this 90 degrees, 180, 270, 360. So that's 90 degrees, 180, 270, and then 360. Now, let's go ahead and use our unit circle to fill in the blanks. So, at 0 degrees, sine is equal to 0. So I'm going to go ahead and graph that. 0, 0. That's 0.1. Okay. Now let's go to 90 degrees. At 90 degrees, sine is equal to 1. Okay. Alright, so at 90, I go up to 1. 91. Alright, and then at 180 degrees, sine is equal to 0 again. Put a dot there. And then I go down to 270 degrees, and sine is equal to negative 1. So I go 270, negative 1, put my dot. And then back at 360, or 0 degrees, sine is again equal to 0. Okay. That doesn't really help me very much. I don't know. I mean, that's like a jagged thing, right? So then I'll go ahead and I'll start putting in 30 degrees. So at 30 degrees, sine is equal to 1/2. So 30 degrees is like a third of this, but we're already at 1/2 the distance to 1. Okay. Let me see. I'm just going to graph the 1/2 because those are pretty easy. And if I go to 135 degrees, I'm at a negative 1/2, right? Where are we at? Oh, wait, nope, sorry. That was the cosine value. Here we go. 150 degrees. I'm at 1/2 again. So if I go to 150, I'm at 1/2 again. Huh. Okay. Here we go. 210, negative 1/2. So at 180, 210, it'd be right around there-ish. So I'm at negative 1/2 at 210. Okay. And then at 330, negative 1/2 again. If I go to about 330 degrees, I'm at negative 1/2 again. So this shows me that this is a bit more of a curve. So I can see there's the graph of sine right there. And it's going to repeat because it's a sinusoid function. We see that from our unit circle. If we just keep extending, we see that with our angles greater than 360 or our angles of depression, that the graph of sine is just going to repeat like that. So I could draw it on the negative over here too. I just have to make sure it passes through those points. And that's the graph of sine. Now, for the graph of cosine, if I were to follow the exact same method, which takes a while, and I were to use all my plots from the unit circle, you can go ahead and compare this on your unit circle. What I would get for y equals, cosine of theta is I would get this at 0. We'll do here 1, 2, 3, 4. That's 90, 180, 270, 360. At 0 degrees, cosine is equal to 1. At 90 degrees, it's equal to 0. At 180, it's equal to negative 1. At 270, it's equal to 0. And then at 360, it's equal to 1. And then if I were to go to negative 90, it'd be equal to 0. And then at negative 270, it'd be equal to negative 1. And then at 180. And then at negative 270, it'd be equal to 0. And then at negative 360, it'd be equal to 1 again. So what we get here for the graph of cosine follows the exact same trend, except at 0, cosine is equal to 1, or it hits the top of our sinusoid. So if you look at sine and cosine, it's the same graph. It's just one is reversed a little bit, or it's behind by a quarter of a period. But it does the same thing. Just so remember, cosine starts at 1, sine starts at 0, and then it's easy. Each quarter section, you just jump to those 4 points, and the sinusoid repeats. Now, these graphs do not always stay the same. They vary. Like for example here. In our book, we see the graph of sine on the left, which is the one we just drew, and then the graph of negative sine, or the inverse. So at negative sine, it's just everything gets flip-flopped. Instead of it being at positive, it's at a negative, and 0 stays the same. And then, so it's the exact same wavelength. It's just the reverse of it. So for at sine, we're still passing through 0. So at 0, we're still at 0, 0, but it goes down instead of going up from the start. So whenever you put a negative in front, you would do the reverse. And then if we did the reverse of cosine, if I wanted to do y equals negative cosine of theta, what that would do is from the start, instead of it being at positive 1, it would be at negative 1. And then it would still go to 0 and then be at positive 1. And so it would just do this. All right, so same graph, it's just reversed. Let's see here, what else are we doing? We're also changing the size of the wavelength on a function, or on a sinusoid function. So what we see here is on both of our examples, we had an amplitude or a top and bottom value of 1 and negative 1. If we want to change that, we want to increase the size of each wave, we just multiply by the distance from 0. All right. So here we see y equals 2 times the sine of theta. That takes the top value to +2 and the negative value to -2. So all we do there is we just increase the value or the height of the function. So if we multiply sine or cosine by a number, that increases the height of the wavelength, and that goes in both directions equally. And now if we wanted to combine that along with doing a negative, it's like if we did -2 cosine of theta, normally cosine of theta would start here at +1. Multiplying it by 2 brings it up to 2, and then multiplying by the negative makes it start at -2 instead of +2. And then we just go ahead and graph it as normal. And then we can also do it in radians as well. Just remember your radian measures. So 0, pi over 2 is 90, pi is 180. 3 pi over 2 is 270, 2 pi is 360. Again, you can either memorize these or you can remember that pi is equal to 180 degrees. 180 over 2 is 90, 180 times 3 over 2 is 270, 180 times 2 is 360, etc. And that's it for graphing sine and cosine. These are sinusoids. It's very, very valuable to memorize these two graphs right here, the initial graph of sine and cosine. If you can't remember them, it's really easy to reconstruct them using those simple rules. And that's it for today's lesson. I'll see you guys in class.